Picture a world so different from the one you know that even the continents would be unrecognizable. No Canada, no Atlantic Ocean, no Rocky Mountains, just one vast, unbroken landmass, stretching from pole to pole, wrapped in heat and silence, and the slow breathing of ancient stone. That is where we are going tonight. Not to any Canada you would recognize on a map, not to a country with provinces and borders and frozen lakes and hockey. We are going much further back, 300 million years further, to a time when the land that would one day become Canada was pressed up against land that would become Africa, Europe, and South America, when everything was one, when the planet itself was still learning what it wanted to be. This is the story of Canada during Pangea, of the ancient rock beneath your feet, the seas that came and went, the mountains that rose and fell before any human eye ever saw them, and the slow, patient work of deep time that shaped everything you know. And tonight, you are going to drift into sleep, carried by that deep time, by the slowness of it, by the impossible scale of it, by the knowledge that beneath every city, every forest, every frozen tundra in Canada, there is rock that remembers a world you can barely imagine. If you find this kind of journey useful, hit subscribe. New sleep documentaries go up every week, and there's always another deep time story waiting for you. Now close your eyes, or let them soften. Breathe slowly, and let the world begin to move. The first thing you need to understand about Pangea is the silence. Not silence in the way we usually mean it, not the absence of sound. There was plenty of sound during the Pangean era. Wind moving across exposed rock, shallow seas lapping against carbonate shelves, the low rumble of volcanic activity in rifting zones, the rustle of early fern-like plants along river margins. All of that existed, but there was no bird song, no mammal calls moving through forest corridors, no insects humming in summer heat in quite the way we know today. The acoustic landscape of the world 300 million years ago was profoundly alien, and the land that would become Canada was sitting inside that alien silence, pressed against continents it would spend the next several 100 million years slowly moving away from. Pangea was not always a single landmass. Before Pangea, there were earlier configurations, older supercontinents with names that sound like spells from another age. Rodinia, Gondwana, Laurentia, the land that would become the core of North America, including much of what is now Canada, was already ancient even when Pangea formed. Much of the Canadian Shield, that vast expanse of exposed Precambrian rock that underlies so much of the country, was already billions of years old when the Pangean configuration assembled itself roughly 335 million years ago. Think about that. The Canadian Shield, which you can still see today, which you can touch with your hand in the wilderness north of Lake Superior or in the hills of Quebec, is among the oldest exposed rock on the surface of the earth. Some of it formed more than 4 billion years ago. When Pangea existed, that rock was already ancient beyond comprehension. It had already survived the breakup of earlier supercontinents. It had already been buried and exhumed, submerged beneath ancient seas and lifted again into air. It was the foundation, the deep keel of what would become North America. And during Pangea, it was sitting in a very different part of the world. Geography during Pangea requires a complete mental reset. The part of Pangea that would eventually become Canada was not sitting at 60 degrees north latitude the way Canada sits today. It was much closer to the equator. During the early Permian period, roughly 290 million years ago, the landmass that would become eastern Canada was positioned somewhere around 30 to 40 degrees north latitude, still well north of the equator, but considerably closer to the tropics than modern Canada, and it was embedded in the interior of a supercontinent. This is crucial to understanding what the climate was like. When you are positioned in the deep interior of a single massive landmass, you are insulated from the moderating effects of ocean currents. You are subject to extreme continental climate conditions, roasting summers, bitter winters, very little rainfall reaching the interior because there is simply no moisture source nearby. The oceans are far away. Much of what would become central Canada during the Pangea period was experiencing conditions that would be deeply unfamiliar to anyone who thinks of Canada as a cold, wet country. Parts of it were experiencing desert conditions, dry, harsh, semi-arid environments where seasonal extremes defined everything living things tried to do. The oceans of the Pangean world were arranged completely differently. There was one great ocean wrapping around the globe called Panthalassa, the universal sea, and there was a smaller inland sea on the eastern side of Pangea called the Tethys Ocean, pressing in between what would become Eurasia and what would become Gondwana. The western coast of Pangea, where the Panthallassic Ocean met the land, was somewhere near the western edge of what would become North America. But the future Canada was far from that coast, buried in the continental interior. Let yourself feel that interior for a moment, the stillness of it. No sea breeze reaching you, just land in every direction, further than anything alive could walk in a lifetime. Vast, silent, ancient. The rock record in Canada is one of the most extraordinary geological archives on the planet. When scientists want to understand what Canada was like during Pangea and the period surrounding it, they read the rocks. Every layer tells a story. Every mineral grain, every fossil fragment, every trace of an ancient shoreline or river channel or desert dune preserved in stone is a sentence in a document that took hundreds of millions of years to write. The Canadian Shield is the oldest chapter in that document. It represents the stable nucleus of what geologists call Laurentia, the ancient core of North America. The rocks of the Canadian Shield preserve evidence of tectonic events going back more than 2.5 billion years. The Acasta gneisses in the Northwest Territories are among the oldest dated rocks on Earth, hovering around 4 billion years old. When you stand on the Shield, you are standing on something that formed when the Earth itself was barely middle-aged. By the time Pangea assembled, the Shield was already the foundation on which everything else was being built. To the east, the ancient Appalachian Mountains were rising as Laurentia collided with the land masses of Europe and Africa. To the south, what would become the interior of North America was collecting layers of sediment. To the west, volcanic arcs were beginning to accumulate along a distant coastline. The Shield watched all of it, stable, ancient, patient. In Quebec and Ontario, outcrops of the Shield rise above thin soils like the bones of the world showing through skin. These are the same rocks that formed long before Pangea, long before life on land, long before anything that would recognize the concept of a continent, and they are still here, still intact, survivors of everything that came after. Breathe that in slowly. 4 billion years of survival, and the rock is still here. Let us talk about the mountains. During the Pangea period, Canada's eastern regions were experiencing the final stages of a mountain-building event that had been going on for tens of millions of years. The collision of Laurentia with the landmasses of Europe and Africa, a collision that helped complete the assembly of Pangea, produced mountains along what is now the eastern edge of North America. These mountains are called the Acadian and Alleghenian Highlands in the geological literature. In their prime, during and just before the Pangea period, they may have been comparable in height to the modern Himalayas. Enormous, jagged, ice-capped peaks stretching from what is now the Maritimes through New England and down the length of the Appalachian chain. The rocks of Nova Scotia and New Brunswick record these mountain building events beautifully. Red beds, the iron-stained sedimentary rocks produced when ancient river systems carried material down from these peaks, are found across the maritime provinces. They represent the erosional debris of mountains that have long since been worn away to their roots. What remains of those great Pangean peaks today is the subdued rolling highland of the modern Appalachians and the ancient rounded hills of the Maritimes, a ghost of something that was once as dramatic as anything on earth today. The violence of that mountain building is worth pausing on. Continental collision is not a gentle process. When Laurentia was pressing against the landmass of Europe and Africa to complete Pangea, the forces involved were staggering. Crust buckling, rock heated deep in the earth being squeezed upward into mountain roots. Earthquakes on a scale difficult to imagine. The noise of it, if you could somehow be transported there, would be beyond anything in modern human experience. But at the geological time scale we are working with tonight, all of that collision and mountain building is happening in slow motion. Press your finger against the table. That is about how fast the continents were moving, barely perceptible, but relentless, absolutely relentless. Let the image form slowly in your mind. You are standing on a high ridge in what will one day be Nova Scotia, but it is 300 million years ago during the Carboniferous period, just as Pangea is completing its assembly. The mountains behind you are immense. Their peaks catch clouds. Glaciers gleam on the upper slopes, even though you are closer to the tropics than modern Nova Scotia sits. The climate here is wet and warm, unlike the dry interior of the supercontinent further to the west. Below you, a vast lowland stretches toward what will eventually become the interior of Canada. Rivers run across it, braided and wide, carrying sediment from the mountains. The rivers drain into swampy coastal lowlands, and in those swamps, something extraordinary is happening. Coal is being made. The Carboniferous period, whose very name means coal-bearing, was the great coal-forming age of Earth history. During this time, vast forests of tree-like plants covered the low-lying, wet margins of the continents. Species like lepidodendron, the scale tree, and sigillaria rose to heights of 30 meters or more. They looked like nothing alive today. They were more related to modern club mosses than to any tree you have ever seen, but they grew to enormous sizes in the warm, carbon dioxide-rich atmosphere. When they died, they fell into the swampy water and were buried before they could rot. Without the bacteria and fungi that would later evolve to break down lignin, the tough structural material in woody plant tissue, these ancient forests accumulated in thick peat layers. Compressed by subsequent sediment, those peat layers became coal. Nova Scotia's coal deposits, particularly around Cape Breton Island, record this Carboniferous swamp world. When you look at a lump of Nova Scotia coal, you are holding compressed ancient forest. You are holding the physical remains of a world that existed while Pangea was forming. When those trees were alive, the continent of Canada as we know it did not exist. There were no Canadian geese, no maple trees, no humans of any kind anywhere on the planet, just towering scaled trees in a tropical swamp, falling and being buried, beginning their slow transformation into the coal that miners would extract hundreds of millions of years later. There is something profoundly quieting about that, about the patience required for coal to form. Let it settle into you as you breathe. The Maritimes during the Carboniferous deserve their own extended contemplation, because what happened there was remarkable even by geological standards. The area of modern New Brunswick and Nova Scotia contains some of the most important fossils of the Carboniferous period in the world. Joggins, Nova Scotia, a coastal site now recognized as a UNESCO World Heritage Site, preserves an extraordinary record of Carboniferous life in its sea cliffs. The cliffs at Joggins expose layer after layer of sedimentary rock, cycle after cycle of ancient coastal swamp environments. Standing trees preserved in the position they grew are found fossilized within the rock. Tracks of early reptiles, the remains of early land animals that were just beginning to conquer the terrestrial environment. When Pangea was assembling, the ancestors of all modern land vertebrates were living in places like Proto-Nova Scotia. Early reptiles, small and lizard-like, were evolving the ability to lay eggs outside of water, the key innovation that would eventually allow their descendants to conquer every terrestrial environment on Earth. The oldest known reptile fossils in the world were found at Joggins. Hylonomus layeli, a small animal no bigger than a modern lizard, was living its life in the hollow trunks of fallen carboniferous trees in what would eventually become Canada when Pangea was young. These animals did not know they were at the beginning of something enormous. They were just surviving, finding food, avoiding predators, breathing the thick, oxygen-rich air of the Carboniferous atmosphere, an atmosphere where oxygen levels may have reached 35% compared to the 21% of today. Higher oxygen supported the enormous insects of the Carboniferous, dragonflies with wingspans comparable to modern seagulls, millipedes more than 2 meters long, scorpions large enough to make a modern person deeply uncomfortable. All of this was happening in what would one day become Canada, in what is now the Maritime Provinces, while Pangea was pressing itself together and the great mountains of the Acadian Alleghenian orogeny were still rising. Breathe slowly. Let the scale of it move through you without resistance. Now we need to move west, across the assembled supercontinent, away from the wet, coal-forming lowlands of the Maritimes and into the vast dry interior. What would become central Canada, the prairies, southern Ontario, and Quebec, much of the interior, was during the Pangean period sitting beneath a broad, relatively flat interior lowland. Unlike the dramatic mountains of the east and the volcanic margins of the far west, the central portion of what would become Canada was a stable platform. The rock beneath it, the ancient shield, provided a rigid foundation. Sedimentary sequences accumulated on top of it in shallow seas during earlier periods, and by the Pangean time those sequences recorded the waxing and waning of interior basins and minor sea incursions. But the deep interior was drying out. As Pangea completed its assembly, the interior of the supercontinent became increasingly isolated from oceanic moisture. Deserts and semi-arid environments spread across vast areas of what would become the mid-continental region. Red beds, those telltale iron-rich sedimentary rocks that form in oxidizing, dry environments, accumulated across portions of the interior. If you were standing in what would one day become southern Ontario during the Permian period, roughly 270 million years ago, you would not recognize it. No Great Lakes, the Precambrian shield visible at the surface in places. To your south, what would eventually become the American Midwest was a vast semi-arid plain. The air was dry. The vegetation was sparse. Small reptiles picked their way across sun-baked ground. The mountains in the east were visible as a distant haze on the horizon, catching what little moisture the atmosphere offered and leaving the interior parched. It was a world of breathtaking desolation in the very best sense. Not dead, but stripped down to essentials, rock and wind and sparse life, and the enormous patient movement of tectonic plates beneath everything. Let us spend some time with the creatures. During the Pangean era, the dominant land vertebrates were not the dinosaurs. Dinosaurs did not appear until after Pangea had already begun to break apart during the Triassic period. During the Permian phase of Pangea, the dominant large land animals were a group called the synapsids. And the synapsids are extraordinarily important because you are one of their descendants. Synapsids are sometimes called mammal-like reptiles, though paleontologists have largely moved away from that term. They represent the lineage that would eventually, after hundreds of millions of years of evolution, produce mammals. And during the Permian period, they were the rulers of the land. In the land that would become Canada, evidence for Permian synapsid, life is fragmentary. The Permian rock record in Canada is not as complete as in other parts of the world, partly because much of the Permian sediment that may have been deposited was subsequently eroded away. But the broader picture from the Pangean world applies to the Canadian portion of the supercontinent. Synapsids of various kinds were moving across the landscape. Some were small, insectivorous animals picking through leaf litter at the bases of sparse Permian plants. Others were larger predators, animals like the famous Dimetrodon, a synapsid with its dramatic sail of bone and skin rising from its back, which lived in environments that spanned the interior of Pangea. Dimetrodon was not a dinosaur. It is not closely related to dinosaurs. It is more closely related to you than to any dinosaur. When you look at a picture of Dimetrodon, you're looking at a distant ancestor, a relative from the deep past, one of the creatures that carried the mammalian lineage forward through the difficult Permian world. Let that sink in as you breathe. Somewhere in the land that would become Canada, your very ancient relatives were walking, picking their way across Permian terrain, surviving, not knowing that their descendants would eventually sit in climate-controlled spaces, thinking about them 300 million years later. The Permian period ended with catastrophe. The end of the Permian, roughly 252 million years ago, was the largest mass extinction in Earth's history. It was so severe that scientists sometimes call it the Great Dying. More than 90% of all marine species and roughly 70% of terrestrial vertebrate species were wiped out. The causes were multiple and are still debated, but the primary driver appears to have been a massive volcanic eruption event in what is now Siberia, a series of eruptions called the Siberian Traps, which released enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere over a period of tens of thousands of years. The resulting greenhouse warming, ocean acidification, and collapse of ocean oxygen levels was catastrophic for life. For the land that would become Canada, the end Permian extinction was a reset. The ecosystems that had been building since the Carboniferous, the forests, the swamps, the communities of synapsids and reptiles and early insects were devastated. The recovery was slow, tens of millions of years slow, but life did recover. It always does, and the recovery brought something new. In the Triassic period, as the survivors of the Great Dying diversified to fill empty ecological roles, a new group of archosaurs, the ancestors of both crocodilians and dinosaurs, began to flourish. And it was in this post-Pangea breakup world that the landscape of what would become Canada began to take on new character. But we are getting ahead of ourselves, because Pangea, while beginning to show the stresses that would eventually tear it apart, was still largely intact as the Triassic began. And the story of the Canadian portion of Pangea did not end at the Permian boundary. It continued, transformed, but continued. There is something we should talk about that often gets overlooked in discussions of Pangea and ancient geography: the sea. During various phases of the Pangean era, shallow seas periodically invaded the continental interior. These were not the deep, cold seas of the modern world. They were warm, shallow, sunlit seas, sometimes barely tens of meters deep, spreading across vast areas of what is now dry land. Geologists call these epicontinental seas, seas that sit on top of continents rather than in deep ocean basins. The Western Interior Seaway, which is one of the most famous examples from North American geological history, came somewhat after the main Pangean period during the Cretaceous, but earlier seaways also existed. During the Devonian period before Pangea, much of what is now Canada was submerged beneath warm tropical seas, and the fossil record of those seas is extraordinary. The Devonian reefs of Alberta, preserved in the rock that now underlies much of the province, record a warm marine world of extraordinary diversity. And during the Pangean period itself, the margins of the continent experienced repeated sea level changes that brought marine conditions in and out of the continental platform. The rock record of the Hudson Bay Basin, the Great Circular Depression in the heart of Canada, preserves sedimentary sequences that record ancient seas washing over the shield. Looking at those rocks today, you can see the ripple marks left by ancient tides, the burrows made by marine invertebrates in shallow mud, the shells of animals that lived when Canada was a sea floor. It is among the most quietly astonishing things in geology that the rock beneath Hudson Bay was once a sea floor, that you could have swum there if you existed then, that the same land that now freezes solid in winter once lay beneath warm sunlit water teeming with life. Breathe slowly. Let the image of ancient seawater moving gently over what is now tundra settle into your mind like something soft. We should talk about the sky. The atmosphere during the Pangean period was different from the atmosphere today. Not dramatically different in composition, but meaningfully different in ways that affected life. Oxygen levels fluctuated significantly across the Carboniferous, Permian, and Triassic periods that span the Pangean age. During the Carboniferous, as we mentioned, oxygen may have reached around 35%, high enough to support those enormous insects. During the Permian, oxygen levels dropped, potentially contributing to the stresses that made the end Permian extinction so severe. During the Triassic, after Pangea began to break apart, oxygen was lower than today. Carbon dioxide levels were also different. During much of the Permian, carbon dioxide was substantially higher than pre-industrial levels, contributing to a generally warmer global climate. There were periods of glaciation during parts of the Permian as well, particularly in what is now Gondwana, the southern portion of Pangea that would eventually become Africa, South America, Antarctica, Australia, and India. But the interior of Pangea remained warm and dry for much of the period. The sky itself would have looked familiar. Blue during the day, stars at night. The stars, of course, were in different positions because the Earth's orientation in space changes slowly over geological time, and because the stars themselves have moved across geological epochs. But a human standing under the Pangean sky would look up and see light, would feel warmth from the same sun, would breathe air that, while having a different oxygen to CO2 ratio, was still fundamentally breathable. The sun rose and set in roughly the same way. The days were slightly shorter. During the Carboniferous and Permian, Earth's rotation was a tiny bit faster than today because the moon has gradually been slowing Earth's spin over billions of years. The difference is small on a human scale, something on the order of 20 to 23 hours per day during the Carboniferous, rather than the 24 we experience now. But it is there. A slightly shorter day, a sky moving just a little faster overhead. Imagine lying on your back in the Permian landscape of what would one day be Canada, watching a slightly faster sky, breathing slightly richer air, feeling the dry heat of the continental interior, the stillness of a world before birdsong. We are now moving into the Triassic period, the time roughly 252 to 201 million years ago. And this is where things get interesting for the Canadian story. Pangea, having assembled over tens of millions of years, was beginning to be stressed. Deep in the earth, mantle convection. Currents that had driven the continents together were shifting. The great supercontinent, having achieved its maximum assembly, was beginning to feel the pull of rifting forces. Cracks were beginning to propagate through the continental crust. magma was beginning to well up along zones of weakness. The breakup of Pangea was not a sudden event. It was as slow as its assembly. Beginning in the Triassic and continuing through the Jurassic and Cretaceous, it took tens of millions of years for the supercontinent to fully fragment into the continents we know today. And for the land that would become Canada, the breakup had profound consequences. The first great rift, the one that would eventually open into the central Atlantic Ocean, began somewhere in the Triassic. The split that would separate Laurentia, the core of North America, from the land masses of Europe and Africa. As this rift widened, the ancient connection between the land that would become Canada and the land that would become Britain, France, and the rest of Europe began to sever. Think about what this means. During Pangea, you could have walked from what would become Canada to what would become Scotland. It would have been an extremely long walk across a continent, but the land was continuous. No ocean between them. No Atlantic, just land. As the Triassic progressed and into the Jurassic, that walking route was closing. A new ocean was being born. Slowly, filled with the first whispers of seawater, an infant Atlantic, barely a few kilometers wide at first, gradually widening as the continents drifted apart at the pace of your fingernail growth. For the Canadian landscape specifically, the Triassic and the beginning of Pangea's breakup brought dramatic changes to the western margin. Throughout the Pangean period, the western edge of what would become North America had been a relatively passive margin, a coastline on the edge of the vast Panthalastic Ocean where sediment accumulated quietly and volcanic activity was relatively limited. But as Pangea began to break apart and ocean floor spreading reorganized the plates, the western margin of North America was transformed. Oceanic crust of the Panthalastic Ocean, carrying volcanic island arcs and oceanic plateaus, began to collide with the western edge of the continent. This collision, which would intensify dramatically through the Jurassic and Cretaceous, began the process of building what would eventually become the Rocky Mountains and the coast ranges of western Canada. But the materials were being gathered long before the mountains were raised. The Triassic rocks of British Columbia record this process in remarkable detail. The Quesnel and Stikine terrains, large chunks of ancient oceanic crust and volcanic island arc material were beginning to approach the western margin of Proto-Canada during the Triassic. They would eventually be accreted, welded onto the edge of the continent, adding new land to what would become British Columbia. Much of western Canada is made of these accreted terrains, pieces of crust that originated elsewhere in the Pacific Ocean and were carried by plate tectonics to be incorporated into North America. When you stand on the mountains of British Columbia today, you may be standing on rock that originated as a volcanic island in the ancient Pacific Ocean, thousands of kilometers from where you are standing. The land does not stay still. The land does not stay put. It wanders. It drifts. It collides and merges and moves again. Let us rest for a moment in the Triassic landscape. It is approximately 230 million years ago. You are standing in what will one day be British Columbia. Pangea is still largely intact, though cracking. The Atlantic has barely begun to form. The climate here, on the western margin of the continent near the ancient sea, is somewhat more moderate than the parched interior. There is moisture. There are plants. But the landscape is strange. In the Triassic, following the great dying of the Permian extinction, life was still recovering. The lush, coal-forming forests of the Carboniferous were gone. In their place, a more sparse vegetation had taken hold. Seed ferns, conifers of unfamiliar kinds, cycads, horsetail-like plants growing along waterways, and moving among the plants, the first dinosaurs. They were small in the early Triassic. unimposing, nothing like the enormous creatures that would come later, but they were there. In what would become British Columbia, Triassic fossils are found in the Nicola Group rocks, marine sediments that record the ancient seafloor of the Panthalassic Ocean along the western margin of the continent. Fossils of ichthyosaurs, enormous dolphin-like marine reptiles, are among the most spectacular finds. The ichthyosaur fossils of British Columbia represent some of the largest marine reptiles ever discovered. Shawnosaurus sicaniensis, found in the Peace River region, was 30 to 35 meters long, among the largest animals that has ever lived in the oceans. These creatures were swimming in the seas just off what would become Canada, while Pangea was cracking and the Atlantic was being born, while the first small dinosaurs were taking their tentative steps on the land. The Arctic. We have not yet talked about the Arctic, and we must, because during Pangea and the period surrounding it, the region that would eventually become the Canadian Arctic archipelago, that vast scattering of islands north of the mainland, was not Arctic at all. During the Permian and Triassic, the land that would eventually drift northward to become the Canadian Arctic was sitting much closer to the equator. The Canadian Arctic islands contain rock sequences, sedimentary formations, that record warm, tropical to subtropical environments. Coal deposits on Axel Heiberg Island and Ellesmere Island in the high Arctic preserve the remains of forests that grew when those islands were subtropical land. The rock tells the story of warm temperatures, lush vegetation, and a very different world. As North America drifted northward following the breakup of Pangea, the land that would become the Canadian Arctic moved into higher latitudes. What had been warm and forested became progressively colder and more austere. The forest gave way to tundra and eventually ice as the northern drift continued. Today, Ellesmere Island is one of the most remote and coldest places in the world. During the Pangean era, it was warm enough to support forests. The coal on Axel Heiberg Island is extraordinary evidence of this. Chunks of coal that form from subtropical swamp forests, now sitting in a region of permafrost and polar bears, speak to the enormous journey the land has taken. Not a metaphorical journey, a physical, measurable, trackable journey across the surface of a moving planet. Let that settle into you as you breathe. The Arctic was once tropical. The land moved. Everything is still moving. We should spend time with one of the most important stories in Canadian geology, the story of what lies beneath the prairies. The Western Canadian Sedimentary Basin is a vast wedge of sedimentary rock that underlies the prairie provinces, Alberta, Saskatchewan, and Manitoba, as well as northeastern British Columbia. It is one of the great hydrocarbon-bearing basins of the world. The oil sands of Alberta are part of its story, the natural gas fields of British Columbia, the potash deposits of Saskatchewan. These resources, which have defined so much of modern Canadian economic history, were formed by processes that trace directly back to the Pangean era and its aftermath. The sedimentary sequences of the Western Canadian Sedimentary Basin record hundreds of millions of years of geological history, from ancient reefs of the Devonian through the warm seas of the Carboniferous, through the slow accumulation of terrestrial sediments as the mountains to the west began rising. The oil sands themselves are a particularly astonishing example of geological time at work. The bitumen in the Athabasca oil sands originated as conventional oil that migrated through rock formations from source rocks formed during the Cretaceous and earlier periods. Over millions of years, as the oil migrated upward and was exposed to bacteria and other degrading processes near the surface, it was transformed into the heavy, viscous bitumen that saturates the sand. What you dig out of the oil sands today is the heavily processed remnant of organisms that lived, died, and were buried tens of millions to hundreds of millions of years ago. You fill a gas tank with the ancient dead, with the compressed and transformed remains of organisms that lived when the world was utterly different, when Canada did not exist as a concept, when the land beneath the prairies was sitting under shallow seas teeming with life. The Jurassic period, 145 to 201 million years ago. Pangea is actively breaking apart now. The central Atlantic has opened enough to be recognizable as an ocean, though still much narrower than today. Gondwana, the southern portion of the old supercontinent, is beginning to fragment. The Indian subcontinent has not yet begun its long journey northward toward Asia. Australia is still attached to Antarctica. And in what is becoming North America, things are changing rapidly. To the west, the collision of oceanic terrains with the continental margin is intensifying. The process that will eventually build the Rocky Mountains is well underway, though the mountains themselves will not reach their full glory for tens of millions of years more. Rivers are beginning to carry sediment from rising western highlands into the interior of the continent. The great seaway that will eventually split North America from north to south, the Western Interior Seaway, is beginning to establish itself. Dinosaurs, which had been small and marginal in the Triassic, are now the dominant large land animals everywhere. In what will become British Columbia and Alberta, dinosaur life is becoming rich and varied. The environments of what would become Alberta during the Jurassic were warm and forested by the standards of what came before and after. Not the lush, coal-forming forests of the Carboniferous, but forests nonetheless, with ferns on the forest floor, with cycads and conifers providing the canopy, with rivers draining from the west and spreading sediment across coastal plains. Dinosaurs were moving through those forests, not the specific famous Alberta dinosaurs of the Cretaceous, those come later, but their ancestors and relatives. Sauropods, the long-necked plant eaters, and early theropods, the predatory lineage that would eventually produce birds, were establishing themselves in the environments of Proto-Canada. The land was filling with life again after the devastation of the end Permian. Life that was rebuilding. Life that was experimenting with new forms. Life that carried the future inside it. We drift now into the Cretaceous. The Cretaceous period, 145 to 66 million years ago, is the era in which the landscape of what would become Canada most dramatically transformed. The Rocky Mountains were rising. The Western Interior Seaway had opened, splitting North America into two land masses separated by a shallow inland sea. And along the western shore of that seaway, in what would become Alberta, one of the greatest concentrations of dinosaur fossils in the world was being laid down. The Horseshoe Canyon Formation, the Belly River Group, the Dinosaur Park Formation. These are the rock formations of the Badlands of Alberta that have yielded Tyrannosaurus rex, Triceratops ancestors, Edmontosaurus, Albertosaurus, Pachycephalosaurus, Ankylosaurus, and dozens of other species that have captured human imagination since their discovery. When you visit Drumheller or Dinosaur Provincial Park in Alberta today, you are walking through the remnants of a Cretaceous floodplain, a warm, forested coastal environment where enormous animals lived, died, and were buried by river floods. Alberta during the Cretaceous was lush, warm, wet, a subtropical to warm temperate environment with forests of flowering plants, because by the Cretaceous, flowering plants had evolved and were spreading rapidly across the world. Magnolias, or figs, early ancestors of plants you know today. The world was becoming more recognizable, even as the animals remained profoundly alien to us. The dinosaurs of Alberta are so abundant partly because the conditions for fossil preservation were so good. Rivers periodically flooded, burying carcasses quickly in fine sediment before they could be destroyed by scavengers and weathering. The floodplains were rapidly accumulating sediment from the rising mountains to the west, and millions of years later, the same rivers that carved the modern Badlands exposed those ancient floodplain deposits, bringing the fossils back to the surface for modern eyes to find. The end of the Cretaceous. 66 million years ago, something fell from the sky. The Chicxulub impactor, an asteroid or comet roughly 10 to 15 kilometers in diameter, struck what is now the Yucatan Peninsula of Mexico with a force that staggered the imagination. The impact released energy estimated at 1 billion times that of the nuclear bomb dropped on Hiroshima. The immediate effects: a fireball that incinerated everything within thousands of kilometers. Enormous earthquakes. A tsunami that circled the globe multiple times. An impact winter caused by the dust and debris thrown into the stratosphere, blocking sunlight for months to years. Acid rain. The collapse of food chains worldwide. For the Canadian landscape, the effects of the Chicxulub impact were devastating. The non-avian dinosaurs, which had dominated Canadian ecosystems for over 100 million years, were wiped out. The lush Alberta floodplains fell silent of their enormous inhabitants. The skies of the western interior seaway, which was by then in the process of draining away, lost the pterosaurs that had soared above the shallow water. The sea itself emptied of the plesiosaurs and mosasaurs that had been its apex predators. What survived tells us something profound about survival. Small animals that could hide underground or in burrows survived better than large ones. Animals that could eat seeds and insects, food that remained available even when the sunlight was gone, survived better than those that depended on fresh vegetation. The small feathered theropods that we call birds survived when their larger relatives did not, and the mammals survived. Small, mostly nocturnal, mostly insectivorous mammals that had been living in the shadows of the dinosaurs for over 100 million years suddenly found themselves in a world with all the large animal ecological roles vacant. The Cenozoic era, the age of mammals, began in what would become Canada as it did everywhere else, tentatively, among small survivors, beginning the slow exploration of a world suddenly emptied of its dominant inhabitants. The Cenozoic in Canada is a story of dramatic climate change, the rise of familiar landscapes, and the long preparation for human arrival. In the early Cenozoic, following the extinction, the world was warm. Warmer than today, much of Canada was covered in lush forests. Fossil forests of the early Cenozoic are found in the Canadian Arctic, including the famous fossil forests of Axel Heiberg Island in Nunavut, where ancient stumps and logs are preserved in near-perfect condition. These forests grew when the Arctic was warm enough to support tall trees. Metasequoia, the dawn redwood, alders, elms, ancestors of modern familiar trees growing at latitudes where today there is only tundra. Mammals were diversifying explosively in these early Cenozoic forests. The ancestral lineages of all modern mammal groups were establishing themselves. Horses, which would evolve in North America, beginning from small, multi-toed ancestors. Bats, whales, which were still land animals at the very start of the Cenozoic and were beginning their return to the sea. Carnivores, rodents, primates. All of these lineages were present or emerging in the early Cenozoic world that included what would become Canada. The continent was still not in its modern configuration. North America and South America were not yet connected. That connection, the Isthmus of Panama, would not form until roughly 3 million years ago. The Atlantic Ocean was widening steadily, but had not yet reached its current breadth. The Rocky Mountains were rising, but had not yet reached their current heights. Slowly, through tens of millions of years of Cenozoic time, the world was becoming more recognizable. The landscapes were becoming more similar to what we know. The animals were approaching something familiar. ice, beginning roughly 2.5 million years ago and oscillating intensely for the past 800,000 years. The Earth entered a series of ice ages. The Pleistocene epoch was an era of advancing and retreating glaciers, and North America was one of the places most dramatically affected. The Laurentide ice sheet, at its maximum, covered virtually all of Canada under a blanket of ice several kilometers thick, from the Atlantic coast to the Rockies, from the Northern Islands to the Ohio Valley in the United States. An incomprehensible mass of ice, so heavy that the land beneath it was compressed downward, literally pressed into the earth by the weight. The rock we have been discussing throughout this entire story, the ancient shield, the Pangean mountain remnants, the Carboniferous coal formations, all of it was buried under ice, and then the ice retreated, multiple times. Between glaciations, Canada was ice-free. Forests grew. Mastodons and woolly mammoths moved across what would become the prairies. Giant ground sloths ambled through forests that are now under the Great Lakes. Camels, which evolved in North America, wandered through ecosystems that looked nothing like modern Canada, but occupied the same geography. The last glaciation peaked roughly 20,000 years ago. By 12,000 years ago, the ice was retreating rapidly, and into the newly deglaciated landscape, following the retreating ice and the animals that moved ahead of it, came human beings. The first peoples of Canada entered a landscape being born, fresh from the ice, new soils, thin and young, new lakes forming in ice-scoured basins, new rivers finding their ways across scraped and gouged terrain. The Great Canadian Shield, exposed again after being buried under kilometers of ice, was slowly being colonized by the first insects, the first plants, the first animals to return. The story of human Canada begins at the end of the longest story we have told tonight. Let us return, in our final contemplation, to where we began. Pangea, the single supercontinent. 335 million years ago, when the land that would become Canada was pressed against the land that would become Britain and Europe and Africa, when the ancient shield was already billions of years old, when the great Carboniferous forests were building the coal that maritime miners would extract hundreds of millions of years later. From that moment of maximum continental assembly, we have traveled through the great dying, through the rise of dinosaurs, through the slow opening of the Atlantic, through the collision of Pacific terrains with the western margin that would build the Rockies, through the extraordinary dinosaur ecosystems of the Cretaceous Alberta floodplains, through the catastrophic impact that ended the Mesozoic, through the Cenozoic forests of the Canadian Arctic when that land was still warm, through the ice ages and the glaciers and the great retreat of the ice, and finally to the first humans entering a freshly deglaciated land. All of this is Canada's deep history, the history that lies beneath the history, the story that was complete before any human voice ever spoke any word about any of it. The rock remembers all of it. The shield remembers the Pangean continental collision. The coal seams of Cape Breton remember the Carboniferous swamps. The Badlands of Alberta remember the Cretaceous floodplains. The drumlins and eskers and glacially scoured lake basins remember the ice. Every time you walk on Canadian ground, you are walking on a library written in stone over 4 billion years, in a language that takes the work of lifetimes to learn to read, but rewards every effort with knowledge of astonishing depth and beauty. The Precambrian Shield. We return to it again because it is the most persistent presence in all of Canada's geological story. It was old when Pangea formed. It was old when the Carboniferous forests grew. It was old when the first dinosaurs walked the land. It was old when the glaciers covered it. It is old now, and it will be old, long after everything human has come and gone. The shield is mostly composed of ancient metamorphic and igneous rocks, granites and gneisses that form deep in the roots of ancient mountains that have long since been eroded away. The mountains are gone, the roots remain, exposed at the surface, smoothed by glaciers, mapped and studied and walked upon and driven across and built upon without most people giving any thought to what they are standing on. In the wilderness areas of the Shield, particularly in the vast boreal forests of northern Ontario and Quebec and Manitoba, you can sit on a rock outcrop and place your hand flat against the surface. The rock is warm from the sun. It is slightly rough under your palm. It may be gray or pink or dark green depending on its mineral composition, and it has been in more or less this configuration, give or take the effects of ice and erosion, for an almost incomprehensible span of time, 4 billion years, or 2 billion, or 3, depending on which outcrop you choose, but in any case far longer than any number the human mind naturally holds on to, far longer than civilization, far longer than our species, far longer than all mammals, far longer than all land plants, far longer than most of the animal kingdom. There is a meditation in that, if you allow it. The rock has been here. The rock will be here. You are briefly here between the rocks, before and after, and that briefness, rather than being diminishing, is somehow clarifying. You are part of a story that is unimaginably larger than you. You are a moment in a narrative that began before the earth had cooled from its formation and will continue until the sun swells and consumes the inner planets billions of years from now. And in this moment, you are warm and breathing and here. That is the entirety of what is required of you tonight. The mountains of the West call for one final contemplation. The Rocky Mountains, the Coast Ranges, the Columbia Mountains, the ranges that define the landscape of British Columbia and Alberta are in geological terms young. They are infants compared to the Canadian Shield. The main phase of Rockies uplift, the Laramide orogeny, peaked roughly 60 to 70 million years ago. The mountains are still being shaped by erosion, by glaciation, by the ongoing movement of the Earth's crust. But their foundations are old. The terrains accreted to the western margin of Canada during the Mesozoic, the oceanic crust and volcanic island, arc material that makes up much of British Columbia, are as old as the Triassic in places, and the sedimentary sequences that were folded and thrust upward to form the main ranges of the Rockies were themselves deposited over hundreds of millions of years, all the way back to the Precambrian. The mountains of the Rockies are, in a sense, ancient sediment being re-elevated, rock that spent hundreds of millions of years on the bottom of shallow seas, accumulating grain by grain, being compressed into limestone and sandstone and shale, and then being caught in the jaws of a tectonic collision and squeezed upward into peaks. The limestone of the Rockies was once seafloor. The same limestone, the calcium carbonate shells of marine organisms that lived in warm, shallow Devonian and Carboniferous and later seas. Those organisms died. Their shells sank to the bottom. They accumulated in layers. The layers became rock. The rock was buried. And then, in the great collision of oceanic terrains with the continental margin, it was thrust upward, lifted, eroded by glaciers during the ice ages into the dramatic peaks and cirques and horns and arêtes that make the Canadian Rockies one of the most visually striking landscapes on the planet. When you see those gray limestone cliffs, you are seeing the compressed shells of marine animals from 350 million years ago, lifted 3,000 meters into the sky. The world is, in the most literal and non-metaphorical sense, profoundly, impossibly beautiful. We are near the end of our journey through deep time. Before we let you drift completely into sleep, let us do one final thing. Let us stand together in imagination in the landscape of Pangea as it was for the land that would become Canada. It is 270 million years ago. The Permian. Pangea is fully assembled. You are standing on the ancient shield, somewhere in what will eventually become the interior of Ontario. The shield is here, as it will always be. Smooth from the erosion of ancient mountains that are now gone. The air is dry. The sky is enormous. To the east, far away, the remnant peaks of the Acadian Alleghenian Mountains catch the afternoon light. To the west, flat land extending as far as you can see, eventually reaching the distant shores of the Panthalasic Ocean without interruption. There are small reptiles moving through the sparse Permian vegetation nearby. A synapsid lifts its head and watches you with eyes that carry no recognition, no understanding, but simply the ancient, patient awareness of an animal alive in its world. It moves on, down to a shallow stream that catches the light. The sun begins to set. It moves slightly faster across the sky than you are used to. The day has been a little shorter. The colors at sunset are the same colors, orange and pink, and the deep blue that comes behind them, because the atmosphere scatters light in the ways it always has. The first stars appear. The constellations are different from what you know. The stars have moved in their slow drift across geological time. But the sky is vast and dark and full of light. The Milky Way is there, a broad river of glow across the zenith, the same galaxy you see from dark sky areas today, beautiful in the same ancient way. A slight wind moves across the Permian land. It smells of dust and rock and the faint vegetable smell of whatever sparse plants are growing nearby. It is not cold, not hot, just the night air of the world moving as it always has. You breathe. The land breathes with you in its own geological way, rising and falling across millions of years as mountains grow and erode and seas come and go. Breathing, patient, alive with deep time in a way no individual organism can fully comprehend. This is Canada before Canada. This is the land at its most ancient and open, before any name was put on it, before any border was drawn, before any road crossed it, or city rose on it, or river was dammed or forest cleared. Just the land, old beyond all reckoning, still and moving at once. Sleep now. Let the deep time settle around you like a blanket, like the slow accumulation of sediment at the bottom of an ancient sea, layer by layer, patient and quiet and unhurried. You are a brief, bright moment in a very long story. You are part of the same matter that makes up the Canadian shield, the same atoms, arranged differently for a little while, alive and aware for a little while, and then rearranging again into other things, as atoms do, as they have always done, as they will continue to do long after anything human remains to observe it. That is not a sad thought. That is the largest, most generous thought available to you. You are made of the oldest stuff. You are continuous with 4 billion years of Earth history. You are not separate from the rock and the sea and the ancient sky. You are a temporary arrangement of the same material thinking about itself in the darkness before sleep. The synapside by the Permian stream does not know this. The Carboniferous scale tree does not know this. The Cretaceous tyrannosaur moving through Alberta floodplain forest does not know this. But you know it. And knowing it, you can rest inside it. Rest now. Breathe slowly. Let the Permian silence fill you. Let the Carboniferous swamp sounds fade into the distance. Let the Cretaceous sun set over the Alberta floodplain and not rise again tonight. Let the glaciers move their slow inches and the Atlantic open its slow millimeters and the shield sit its patient billions of years. Let all of it happen at geological speed, unhurried, inevitable, beautiful in its slowness. You are safe. You are warm. You are resting on rock that has been here for 4 billion years and will be here long after you wake. The ground beneath you has survived everything, has been through it, everything. And it is still here, still solid, still carrying everything that walks or grows upon it. Rest on the ancient ground. Let the deep time carry you. The next breath is enough. The next breath is all that is needed. And then the one after that, slow, still, deep. If this journey helped you find rest tonight, subscribe so you do not miss the next one. Every week, a new exploration through deep time, through forgotten worlds, through the geological story of the earth that lies beneath everything you know. The next story is already waiting. Sleep well. There is a geological concept called unconformity. It refers to a gap in the rock record, a place where layers of sediment are missing, either because they were never deposited or because they were eroded away before the next sequence of layers was laid down. When a geologist reads a sequence of rock and encounters an unconformity, they encounter absence. A silence in the geological record. Time that passed but left no layer to show for it. Canada's rock record is full of unconformities, gaps that span millions, sometimes hundreds of millions of years. The Precambrian shield itself, where it is exposed, is often immediately overlain by Cambrian or later sediments, with a gap of hundreds of millions of years represented by nothing but an erosional surface. An unconformity so vast that geologists gave it a name: the Great Unconformity. The Great Unconformity is visible in places like the Grand Canyon in the United States and in outcrops across the Canadian Shield. It represents somewhere between 500 million and 1.25 billion years of missing time, depending on the location. Rock that may have been deposited but was eroded away, or a period when no sediment accumulated. Either way, gone, as silent as sleep. There is something beautiful about the Great Unconformity in the context of a sleep documentary about geological deep time. It is a record of forgetting, of time that passed without leaving a complete account of itself. The rock slept, in a sense, through some of its own history. The record has gaps, and yet the story continues anyway after the gap, picking up where it left off, carrying forward the thread of Earth history through whatever interruption the unconformity represents. Your sleep is like that, a small unconformity in your own personal record, hours that will pass without a complete account of themselves. And when you wake, the story continues, picks up, carries forward. The rock does not mourn its unconformities. The story continues regardless. Hudson Bay. We have mentioned it in passing, but it deserves its own sustained attention, because Hudson Bay is, among other things, a direct record of the weight of ice. Hudson Bay is surprisingly shallow for its size. The average depth is only about 125 meters, quite shallow compared to most major ocean bodies. Part of the reason for this shallowness is that the land around and beneath Hudson Bay is still rebounding from the weight of the Laurentide ice sheet that covered it until roughly 8,000 years ago. The technical term is isostatic rebound. When the ice melted, the removal of its colossal weight allowed the crust to begin rising back up, like a mattress recovering when someone gets off it. The process is still ongoing. Parts of the Hudson Bay shoreline are rising at rates of more than a centimeter per year. This means that the shape of Hudson Bay is still changing, still evolving, still recovering from the ice. The coastlines that indigenous peoples have known for thousands of years are not the same coastlines that existed when the first peoples arrived in the region after deglaciation. The land is still moving, and the rock beneath Hudson Bay, the ancient shield, carries memories that go far deeper than the ice. Beneath the glacial sediments and the shallow marine sediments deposited since deglaciation, there are Precambrian rocks of extraordinary age, the ancient basement of the continent, unchanged in their essential character since long before Pangea, since long before life on land, since long before the first fish in the ocean, as old as anything on earth. Hudson Bay sits on top of some of the most ancient rock on the planet. Above it, the cold northern water. Around it, the boreal forest and tundra. Below it, rock that was already ancient when the earliest forms of multicellular life were experimenting with what it meant to be more than one cell. Breathe slowly. Let the image settle. The cold water, the ancient rock below. The ice that came and went and is coming and going still, somewhere in the geological conversation that never entirely ends. Let us talk about water. Canada has more fresh water than almost anywhere else on Earth. The Great Lakes, shared with the United States, contain roughly 21% of the world's surface fresh water. The lakes and rivers and wetlands of the Canadian Shield hold immense quantities more. The rivers of Canada drain into 3 oceans. The Mackenzie River draining into the Arctic. The St. Lawrence and its tributaries draining into the Atlantic. The Fraser and Columbia systems draining into the Pacific. Where did all this water come from? The quick answer is the ice. The glaciers deposited enormous quantities of meltwater as they retreated, carving basins and filling them. The Great Lakes basins themselves were carved by glacial erosion, scoured out of the rock over multiple glacial cycles. Before the ice ages, the Great Lakes, as we know them, did not exist. The rock was there, the shield was there, but the specific arrangement of water in those basins was created by ice. But water itself, as a planetary resource, goes much further back. The water on Earth arrived billions of years ago, partly from the planet's own interior volcanic outgassing, and partly from comets and asteroids that delivered icy material during the early solar system. The hydrogen and oxygen atoms in every drop of water in the Great Lakes have been on this planet for most of its history. They were here during Pangea. They were here before Pangea. They were cycling through the oceans and atmosphere and rock of the early Earth long before life emerged. The water you drink was in the Permian Sea, was in the Carboniferous swamp, was cycled through the bodies of dinosaurs and the roots of Carboniferous trees and the ancient bacteria of the Precambrian ocean floor. The same water, always the same water, moving, cycling, returning. Tonight, as you sleep, water moves through your body on its ancient circuit, old as the earth, going where it needs to go. The fossils. Canada is extraordinarily rich in fossils, and each fossil site tells a story that connects directly to the Pangean world we have been exploring tonight. The Burgess Shale, discovered in 1909 by Charles Doolittle Walcott in the mountains of British Columbia, is one of the most important fossil sites in the world. It preserves the soft-bodied marine animals of the Cambrian period over 500 million years ago in extraordinary detail. Organisms without skeletons, without hard parts, whose bodies normally decay completely and leave no trace, are preserved here in fine-grained shale in such detail that you can see their guts, their eyes, their appendages. These animals lived in a world even further removed from Pangea than Pangea is from us. They lived before the great Pangean mountain-building events, before the Carboniferous forests, before the first vertebrates crawled onto land, before any of the events we have described tonight. They lived in a Cambrian sea that covered part of what would eventually become the Canadian Rockies. What the Burgess Shale teaches us, among many things, is how deep the story goes. We have been focused on the Pangean period tonight, on 300 to 400 million years of geological history, and that already felt impossibly vast. But the Burgess Shale is 500 million years old. The Canadian Shield is older still by a factor of 4 or 5 or 8, depending on which part of it you measure. The story keeps getting longer the deeper you look. There is no bottom to it, no point at which you reach something that is not itself a continuation of something older. The universe is 13.8 billion years old. The Earth is 4.5 billion years old. And the thread of causes and effects that led to this moment, to you reading or listening to these words, stretches back without interruption to the beginning of everything. You are the latest edge of an unbroken story. There has never been a gap in the chain that led to you. Not for a single moment, not for a single atom's worth of pause. The Devonian. We keep returning to geological periods in our journey because each one adds texture to the deep history of the land. The Devonian, approximately 419 to 359 million years ago, predates Pangea, but is crucial to understanding what Pangea was built upon. During the Devonian, what is now Canada was partly submerged beneath warm tropical seas. The Devonian reefs of Alberta, now preserved in the subsurface, were among the largest reef systems ever to exist on Earth, comparable in scale to the modern Great Barrier Reef, stretching across thousands of kilometers of warm carbonate shelf. These Devonian reefs are not visible at the surface today. They are buried under younger sediment, often thousands of meters deep. But they are still there. The oil and gas reservoirs of Alberta exploit them, because the porous reef rock makes excellent reservoirs for hydrocarbons that migrated into them from adjacent source rocks over millions of years. The Devonian is also the period when plants truly conquered the land. During the Devonian, the first forests appeared, simple at first, with no trees reaching more than a few meters, but increasingly complex as the period progressed. By the late Devonian, the first true trees had evolved, woody plants with deep root systems and tall canopies, changing everything about how water and nutrients move through the landscape, changing the atmosphere by consuming carbon dioxide and releasing oxygen, changing the rock by accelerating the weathering of mineral surfaces through root action. Plants change the world. They change the climate. They set in motion the chain of events that would produce the carboniferous coal swamps and the oxygen-rich atmosphere that supported the giant carboniferous insects. They created the conditions that made it possible for vertebrates to move onto land, and eventually, in tens of millions of years, become the ancestors of everything that walks or crawls or climbs or flies today. The first plants to truly colonize the Canadian landscape did it in the Devonian, long before Pangea was complete, long before anything we would recognize as a Canadian forest, but making the land ready, setting the stage. There is something we should consider about the nature of what we are doing tonight. We are using language, which is a technology that has existed for, at most, a few 100,000 years, in even its most rudimentary form, to reach back through geological time and attempt to evoke a world that predates language by hundreds of millions of years. The Permian synapside by the stream did not have language. The Carboniferous scale tree did not have language. The first tentative plants to colonize the Devonian landscape did not have language. Language is, on the geological timescale, an absolutely brand new thing. So new that it barely registers. So new that in the context of the Canadian Shield's 4 billion year history, the entire span of human language, the entire accumulation of everything ever said or written in any language by any human, is a rounding error. And yet, here we are, using it, building these images in your mind, sending them across whatever distance separates the person speaking these words from the person hearing them. Using this extraordinary, fragile, unimaginably young tool to touch something as old as the planet itself. There is a kind of miracle in that, a kind of absurd, beautiful miracle, that this thin film of intelligence and language and culture that we call human civilization has managed to read the rock well enough to see back into time, to reconstruct the shape of Pangea, to know the heights of the Acadian mountains, to understand the chemistry of the Carboniferous atmosphere, to hold in our minds, even briefly, even imperfectly, the enormity of the story written in the stone beneath our feet. We are the only things on earth, as far as we know, that can do this. The only beings on this planet capable of reaching back past their own memory, past their own species, past all the extinctions and upheavals and slow geological revolutions, and seeing, even dimly, where we came from and what was here before us. That is not nothing. That is remarkable. The boreal forest, taiga, the great northern forest that covers more than half of Canada, spruce and fir and pine and larch, the largest terrestrial biome on Earth, an almost incomprehensible expanse of trees stretching from Newfoundland to the Yukon to the Northwest Territories. The boreal forest is young by geological standards. It assembled itself after the retreat of the last glacier. The tree species that make it up evolved long before, during various phases of the Cenozoic, but their specific configuration in Canada's post-glacial landscape is geologically very recent. The boreal forest as it exists today is on the order of thousands of years old, not millions. But the land beneath it is ancient. The shield rises through the boreal in countless places. Rounded knobs of Precambrian granite interrupting the forest, lakes in glacially scoured basins, bogs and fens developing in low-lying areas where drainage is impeded by the shallow soils over impermeable bedrock. The boreal forest is a thin living layer over very old rock. Standing in the boreal forest at night, you can feel both the youth of the living world around you and the antiquity of what lies beneath. The spruce are maybe 100 years old, maybe 200 in older stands. Young, growing and dying and regrowing in cycles measured in decades. The rock they grow out of is 100 million times older. 200 million times older. The forest is a fleeting shimmer on top of something permanent. And in the silence of the boreal night, there is a quality of stillness that seems to know this. The trees do not move unless the wind moves them. The lakes lie flat and dark. The stars are thick above where there are clearings. And somewhere beneath all of it, the shield is there, patient, old, carrying everything. Let us consider the future. We have been traveling through the past all evening, through Pangea, through the Carboniferous and Permian and Triassic and beyond. But the same processes that have shaped Canada's geological history are still ongoing. Plate tectonics did not stop when humans arrived. It continues. The Atlantic Ocean is still widening. North America and Europe are moving apart at roughly 2 centimeters per year. Not perceptible in a human lifetime, not perceptible in the entire span of recorded history, but over geological time, enormous. In 100 million years, the Atlantic will be significantly wider than it is today. The Rocky Mountains are still being eroded. Rain and ice and rivers are still carrying material from the peaks into the valleys and eventually into the ocean. The Rockies are not as high as they once were. They will not be as high in another 50 million years. Their erosional debris is accumulating on the ocean floor off the Pacific coast, slowly. The Canadian shield is still rising, very slowly, from the removal of glacial weight. The land of Hudson Bay is still rebounding. The planet is still responding to what the ice ages did to it. And in the deep interior of the Earth, the mantle convection that drives plate tectonics continues. In the far geological future, the continents will rearrange themselves again. Various models predict that in 200 to 300 million years, the continents will converge into a new supercontinent, various named configurations in different models. Pangea, Proxima, Novopangea, Amasia. The specific configuration is uncertain, but the principle is well established. Continents have formed supercontinents before. There is reason to think they will do so again. Canada's rocks will be part of that future supercontinent. The shield will still be there. Old then, as it is old now. As it was old during Pangea, it will have outlasted another complete Wilson cycle, the full sequence of supercontinent, assembly, and breakup that takes roughly 500 million years to complete. The shield abides. Salt, the Windsor, salt deposits of Nova Scotia and Ontario, the Elk Point group evaporites of Western Canada, the ancient salt beds that underlie parts of the Prairie Provinces and the Maritimes. These salt deposits formed when ancient seas evaporated. In the Devonian and Silurian periods, shallow seas covering parts of what would become Canada evaporated in warm, arid conditions, leaving their dissolved salts behind. Layer by layer, the salt accumulated, was buried under subsequent sediments, and was preserved. When you use salt on your food, you may be using salt that was dissolved in a Devonian sea. Salt that was crystallized when what is now Ontario was covered by a shallow tropical ocean. Salt made from the same water that fish were swimming in, that reefs were building through, that corals and trilobites and crinoids were living their entire lives within, 380 million years ago. Salt is one of the most fundamental and ancient substances in the human experience. Humans have harvested salt for as long as there have been humans, traded it, fought over it, named cities after it. Prague and Salzburg and many others are named for salt, and yet the salt we use today often formed in seas that ceased to exist before the first tetrapod crawled onto land. The ordinary contains the ancient, always, in everything. The final image. You are very close to sleep now. Your breathing has been slowing for some time. The words have been finding less resistance as they come. The thoughts are becoming less distinct. The geological time we have been moving through is becoming less a narrative and more a sensation. A feeling of depth, of age, of something large and patient, underlying everything. Let the last image be this. Somewhere in the Canadian wilderness, on a late summer evening, a person is sitting on a rock outcrop overlooking a lake. The lake is in a glacially scoured basin. The rock they are sitting on is Precambrian granite. There are jack pines at the edge of the outcrop, growing from thin soil. The evening star has appeared over the western tree line. The water of the lake is perfectly still. The person puts their hand flat on the granite. They feel its warmth, held from the day's sun. They feel its roughness, its solidity. And they know, because they have thought about it before, that the rock under their palm formed long before any life with a spine existed on this planet, that it has been through everything, that it will be here long after they are gone. And rather than feeling small in the face of that, they feel the opposite. They feel connected. They feel like part of something continuous, something that does not begin or end, but simply continues, changing form, rearranging, always the same fundamental stuff in new configurations. The evening deepens, the star brightens, the lake reflects it, the granite holds the warmth of the sun. Everything is all right. Everything is, in the deepest sense, all right. Sleep now. Let the story fold itself closed for tonight. The geological narrative will be here when you wake. The shield will be under your feet. The ancient will still be ancient. The deep time will still be deep. But for now, let all of it soften. Let the Pangean landscape dissolve. Let the Carboniferous swamp go quiet. Let the Permian interior dry up into something softer than wind. Let the Cretaceous floodplain fall into evening. Let the Triassic Sea recede. Let the ice advance and then retreat very slowly, so slowly you cannot see it moving. Let the world be old and patient all around you. Let your breathing slow to the pace of geological time. One breath for every 1,000 years. One breath for every period. One breath for every eon. You do not need to go anywhere. You do not need to think anything. You do not need to do anything except breathe. The rock is under you. The ancient is with you. The story is complete for tonight, even though the story itself never ends. Rest in the deep time. Rest in the knowledge that you are part of something that began 4.5 billion years ago and has not stopped for a single moment since. Rest in the shield. Rest in the slow. Rest. The rivers. Before we let you go entirely, we should spend time with the rivers, because the rivers of Canada are among the most direct physical connections between the geological past we have been discussing and the world as it exists tonight. The Mackenzie River is the longest river in Canada and the second longest in North America. It drains into the Arctic Ocean through a vast delta, and its watershed encompasses an enormous portion of northwestern Canada. The Mackenzie flows through rock of multiple geological ages. Its headwaters drain from the mountains of British Columbia and the Yukon. The young Cordilleran ranges built from accreted terrains and uplifted sedimentary sequences during the Mesozoic and Cenozoic. Its middle reaches flow across the interior plains, through rocks of the Western Canadian Sedimentary Basin, through the ancient shallow sea sediments and Devonian reef deposits and Carboniferous formations. Its lower reaches cut through material shaped by glaciation and permafrost. The Mackenzie is, in a sense, a timeline, a river that cuts through geological time as it flows toward the sea. The water in it has fallen as rain on rocks of wildly different ages, has dissolved minerals from Precambrian basement and Cretaceous shales and Quaternary glacial deposits, has carried a sediment load that is a mixture of geological ages, all ground together and transported northward toward the Arctic. The water flowing in the Mackenzie tonight has been on a long journey. Some of it fell as snow on the Canadian Rockies. Some drained from boreal forests underlain by shield. Some emerged from springs that have been flowing since the last ice age. All of it is moving. All of it is going somewhere. All of it is part of the same ancient cycle that has been moving water around this planet for 4 billion years. Water falls. Water flows. Water reaches the sea. Water evaporates. Water falls again. The rivers do not stop. The rivers do not wait. The rivers simply continue. Let us talk about the silence beneath the noise. If you go far enough into the Canadian wilderness, far enough from highways and aircraft corridors and any human infrastructure, you can hear a silence that is qualitatively different from the silence in a room or a quiet building. It is a natural silence, an active silence, full of small sounds, wind in trees, water moving over rock, the calls of birds and insects that are themselves so consistent they become part of the silence rather than interruptions to it. But beneath even that active natural silence, there is something deeper, something that cannot quite be heard, but can sometimes be felt. The silence of geological time, the silence of rock that has been doing what it does for billions of years without anything like noise as we understand it, without any sound that carries meaning to a listening ear, because there was no listening ear for billions of years. The shield is silent in that way, the deepest silence there is, the silence of process without observer, of change so slow it cannot be heard even if you had ears to hear it, of molecules migrating through crystal lattices, of isostatic rebound measured in millimeters per year, of erosion 1 grain at a time. That silence is always there, underneath everything. underneath the bird song and the river sounds and the wind, underneath the city noise and the traffic sounds and the human voices, underneath the sound of your own breathing, the geological silence, the deep time quiet. If you can find it tonight, even briefly, it is one of the most restful things that exists. To rest in the geological silence, to let the billions of years hold you, to stop being a person in a moment and become, very briefly, part of the deep story. You do not have to earn that. You do not have to understand all of geological history to rest in it. You just have to let go of being in a hurry, let go of the immediate, let go of the measured seconds, and breathe into something larger. The shield is there. It will be there. It has always been there. Rest in the geological silence. Alberta. We have visited it several times tonight because Alberta's geological story is extraordinary. But there is one more thing to say about it before we close. Alberta contains, within its boundaries, evidence from virtually every major period of Earth's geological history. The Precambrian shield influences the deep subsurface. Paleozoic sedimentary sequences, including those extraordinary Devonian reefs, underlie the plains. Mesozoic formations, including the Cretaceous dinosaur beds, are exposed in the Badlands. Cenozoic sediments record the time after the dinosaurs, and glacial deposits cover much of the surface, recording the ice ages. If you dug straight down through the land of Alberta, you would be reading geological history backward, through the glacial tills, through the Cretaceous Badlands, through the Jurassic and Triassic sediments, through the Permian and Carboniferous and Devonian sequences, down to the Precambrian basement at the bottom. You would be drilling through hundreds of millions of years of time, through seafloors and river deltas and ancient soils and buried reefs, through the entire span of complex animal life on Earth. The land of Alberta is a library and a time machine simultaneously. Every well drilled for oil and gas, every quarry, every river cut through the plains is a window into a different part of that vast geological library. And the scientists who read those windows have spent over a century reconstructing the history of this place, adding detail and nuance and depth to our understanding of what Canada was like before Canada existed. The dinosaurs of Alberta are the most famous story, but they are one story among hundreds. Every fossil fish from the Devonian reef system, every coral specimen from the Carboniferous, every piece of Permian red bed, every Triassic bone fragment, they are all chapters. They are all voices speaking from the deep past into the present. Tonight you have heard some of those voices. Let them settle into your sleep as something quiet and good. Granite. We should end with granite, because granite is perhaps the most quintessentially Canadian rock. The great gray and pink and speckled outcrops of the Canadian Shield. The rock that defines the Canadian wilderness in a way that no other material does. Granite forms deep in the earth, kilometers beneath the surface, from the slow cooling of magma. The crystals in granite, the feldspar and quartz and mica and hornblende, grew over millions of years as the magma cooled in the darkness under enormous pressure. When the granite crystallized and became solid rock, it was buried. It took tens of millions more years of erosion of overlying rock to expose it at the surface. The granite you can touch in the Canadian wilderness today spent most of its existence in complete darkness, under enormous weight. It has only been at the surface, exposed to air and light, for a tiny fraction of its total existence. It formed in darkness. It lived in darkness. It was revealed by the slow erasure of everything above it. And now you can put your hand on it. Now, in this remarkably brief and geologically anomalous moment, it is exposed at the surface, in the light, touchable. Enjoy that. Every time you touch the granite of the Canadian Shield, you are touching something that spent billions of years in total darkness under several kilometers of rock, waiting, completely unaware that it was waiting to be at the surface. And now it is. And you are here, and your hand is on it. The improbability of that meeting is staggering. Your hand, that rock, this moment, requiring 4.5 billion years of exact events to arrive at, and yet here it is. Here you are. Breathe. The granite is patient. It does not need you to understand it. It simply is, what it has always been, what it will continue to be. But you can rest against it for a while. You can let it hold you for a while. And tonight, as you sleep, you can rest knowing that the ancient is underneath you, that the deep time is holding you, that the rock remembers everything that has ever happened on this piece of land in its patient mineral way. The shield is there, the story is long, and you are part of it. Rest now, sleep well. This has been a journey through the deep time of Canada, from Pangea to the present, from the ancient shield to the first ice and the first people, and the world as we know it. If you found rest in these deep time stories, subscribe and join the next journey. There is always another story written in the rock, always another ancient world waiting to be remembered. Good night. There is a quality to the Canadian landscape that geologists sometimes call physiographic character. The way the land has been shaped, not just by its rock type, but by the long accumulation of geological events that produced it. Canada's physiographic character is, more than almost any other country on Earth, defined by its bedrock. The great physiographic regions of Canada are essentially geological regions. The Canadian Shield dominates the center and east. The Western Cordillera, that long spine of mountains and plateaus, defines the west. The interior plains, the prairies, sit between them. The Arctic lowlands spread across the north. The Hudson Bay lowlands cup the bay. The St. Lawrence lowlands carry the weight of the most densely populated region in the country. Each of these regions has a distinct character that flows directly from its geology. The Shield is rocky, thin-soiled, lake-studded, because the glaciers stripped it, and the thin soils that have formed since have had only a few thousand years to accumulate. The prairies are flat and fertile, because they formed from the sediment of ancient seas and the deposits of glacial outwash, and because they are underlain by soft, sedimentary rock that weathers to rich, agricultural soil. The mountains of the West are dramatic and high because the collision of oceanic terrains with the continental margin is relatively recent, and the uplift that created them has not yet been overcome by erosion. You live in the physiographic character of Canada if you live in Canada. It shapes what you see when you look out your window, whether you look at rock or prairie or mountain or forest. All of that is the visible expression of geology, the surface manifestation of everything we have been discussing tonight. The landscape is not arbitrary. It is the result, the consequence of everything that happened before. Every rock forming and eroding, every sea advancing and retreating, every glacier advancing and retreating, every tectonic collision and rifting, all of it landing eventually as the specific place you live, the specific view from your window, the specific ground under your feet tonight. Nothing in the landscape is arbitrary. Everything has a reason that goes back, if you follow it far enough, to the beginning of the earth. Tectonics and sleep share a quality that is worth noticing before we go. Both are processes that happen below awareness. You do not direct your sleep. You do not choose moment by moment what stage of sleep you're in, or what your brain does during it, or how your body repairs itself in the dark hours. Sleep happens to you. It carries you somewhere that your conscious mind cannot follow, does its work, and returns you. Tectonics is like that, the great churning of the mantle beneath the crust. the slow convection of rock so hot it flows over geological timescales like very thick fluid, driving the plates, moving the continents, building and destroying mountains, forming and fragmenting supercontinents. None of this requires anyone's attention. None of it requires direction or intention. It simply happens, driven by the physics of a cooling planet and the geometry of convection cells in a viscous medium. It has been happening for 4.5 billion years without pause, without a controller, without oversight, and the results are everything: the Shield, the Rockies, the Atlantic Ocean, the Canadian prairies, the coal of Cape Breton, the oil of Alberta, the fossils of the Burgess Shale, and the Badlands of Alberta, and the cliffs of Joggins. All of it merged from an unattended process, from physics running itself according to its own rules, in the dark, without anyone watching. Your body does something similar in sleep. The unattended processes run. The consolidation of memory happens. The cellular repair happens. The hormone cycles complete themselves. The brain does its housekeeping in the dark. Trust the process tonight, the way you would trust the planet's processes if you thought about them. You do not have to manage your sleep. You do not have to hold on to it. You just have to let go of what keeps you from it. The process knows what to do. The deep process always knows what to do. We have been moving through enormous amounts of time tonight. 300 million years, 400 million years, 4 billion years, numbers that have no real referent in human experience. There is a technique sometimes used to make geological time comprehensible, compressing it, imagining the entire history of the Earth as a single calendar year, a metaphor popularized by Carl Sagan and others. If Earth's history were 1 year long, the planet would form on January 1st. Simple cellular life would appear in February or March. Complex multicellular life would not appear until mid-November. The first fish would appear in late November. The first land plants in early December. The carboniferous coal forests would burn briefly through mid-December. Pangea would assemble and begin breaking apart in the third week of December. Dinosaurs would rule the earth from about December the 24th through the morning of December 30th, when they would disappear. Humans would appear at about 11:58 on December 31st. Written human history would occupy the last few seconds of the year. You are reading or listening to these words in the last few seconds of December 31st. The Pangean world we have been exploring tonight was mid-December. The Canadian Shield has been here since late January. These numbers do not quite enter the body as felt experience. They remain to some extent conceptual. But sitting with them in the quiet before sleep, letting them move through you without grasping for comprehension, can produce something useful. A softening of the usual sense of urgency. A relaxation of the feeling that everything matters with equal weight. Right now, when you sit beside deep time, the immediate loses some of its grip. The Shield has been here since late January. In the calendar. Year of the Earth, you are existing in the last few seconds of the last day. And in those few seconds, you can breathe slowly and not be in a hurry, because the year has been very long and is still going, and there's no need to rush any particular moment of it. Before the very final breath, one more thing. There is a beach in the Northwest Territories. More than one, but let us think of one particular beach. On the shore of a lake in the Slave Creighton, one of the most ancient parts of the Canadian Shield. A beach made of sand that eroded from rocks that are nearly 4 billion years old. If you pick up a handful of that sand and look at the individual grains, you're looking at fragments of some of the oldest rock on the surface of the earth, ground down over geological time by water and ice and wind, reduced from enormous mountain roots to tiny grains. individual grains of a casta gneiss among the oldest rocks ever dated. And someone sat on that beach, or walked along it, or simply moved through that landscape without stopping, without knowing exactly what they were walking on, living their life in the subarctic without any particular reason to think about 4 billion-year-old sand. The ancient does not demand recognition. The deep time does not require acknowledgement. It is there whether you know about it or not, whether you think about it or not, whether any human has ever walked there or not, but knowing it changes something. It changes the texture of existence slightly. It adds depth to the ordinary. It makes a handful of sand something remarkable. It makes the ground under your feet, wherever you live, part of a story so large that telling it takes billions of years and a universe old enough to have time for it. You know it now, or you have been reminded of it if you knew it before. Carry it lightly. You don't need to think about it to have it. It will be there in the background of things, adding its quiet weight of antiquity to the ordinary moments of ordinary days. And on nights like this one, when you want to let it come to the foreground and carry you to sleep, it will do that too. The ancient is very good at holding things, at carrying things, at being patient with the brief, bright moments that happen on its surface. Let it hold you tonight. Sleep well. Sleep deep. Sleep in the deep time. Rest in the knowledge that 335 million years ago, the land beneath you was part of something vast and connected and different in every visible way from what it is now. Rest in the knowledge that the rock remembers all of it, even when no one asks it to. Rest in the knowledge that 4 billion years of change have brought you to exactly here, exactly now, and that this moment, however ordinary it feels, is the result of the most extraordinary and improbable sequence of events imaginable. You are an improbability that happened anyway. You are a brief pattern of atoms that has had the remarkable experience of being aware. You have thought about Pangea tonight. You have held for a little while the image of a world before Canada, a world of one great continent and one great ocean, and the slow, silent work of geological forces shaping everything. And now you can let that image soften, can let the supercontinent drift apart, and the oceans fill in, and the mountains rise and fall, and the ice come and go, and the forests spread across the land, and the first peoples arrive, and all of human history unfold in its brief, glorious span, and still know that beneath all of it, the rock is there, the shield is there, the ancient is there, and you are here, for now, for this warm, breathing, thinking while, for this good and ordinary miracle of a night. Good night. One more section of deep time before the silence takes over completely, because there is one part of Canada's geological story we have moved past too quickly, and it deserves its own quiet contemplation tonight. The Yukon. The Yukon Territory is in many ways the most geologically complex region of Canada, and part of its complexity comes from something that happened during the Pangean era and its aftermath that is unique in the Canadian story. When the great ice sheets of the Pleistocene covered virtually all of Canada, one region escaped complete glaciation. Pangea, the ancient land bridge that connected Asia to North America across what is now the Bering Strait, remained largely ice-free during the major glaciations. And the interior of the Yukon, sheltered by mountain ranges that captured the precipitation that would otherwise have fed glaciers, also remained relatively ice-free. This meant that the Yukon was a refuge, a place where life persisted through the cold ages when much of the rest of Canada was buried under kilometers of ice. Mammoths roamed there. Horses, which had evolved in North America over tens of millions of years, survived there when they were being driven to extinction. Elsewhere on the continent, cave lions, scimitar cats, ground sloths, a remarkable megafauna that survived in the Yukon's ice-free interior when the same animals were being pushed out of the glaciated south. The permafrost of the Yukon preserves these animals in extraordinary condition. Frozen specimens are periodically discovered in river cut banks and mining operations. Mummified horses, preserved bison, baby mammoths with their fur still intact. Animals that lived 20 or 30,000 years ago, preserved as if they only recently died, because the permafrost has kept them frozen ever since their burial. These frozen animals are windows into a world that is recent by geological standards, but completely alien in terms of the living community it contained. The Yukon of 20,000 years ago looked more like the African savanna of today than it looks like the modern Yukon. Large herds of grazing animals, multiple species of large predators, an ecosystem of a richness and diversity that has not existed in North America since the Pleistocene extinctions removed most of the large mammals. Why they went extinct is a question that has been debated for decades. Climate change as the glaciers retreated, habitat transformation as forests replaced the cold grasslands that supported the megafauna, the arrival of human hunters who had never encountered these animals, and against whom the animals had no evolutionary defense. The answer is probably some combination of all of these. The end result was the same: a continent emptied of most of its large mammals in geological terms, very recently, within the last 12 to 15,000 years. The Yukon's permafrost holds the bodies of those animals, preserved, waiting, speaking to us about a world that existed before the most recent chapter of Canadian history began. The permafrost itself. Permafrost is ground that has been continuously frozen for at least 2 years, though in practice much of Canada's permafrost has been frozen for hundreds or thousands of years. It underlies roughly half of Canada's land area. In the far north, it can extend to depths of several hundred meters. The permafrost is not inert. It is extraordinarily rich in organic material. The dead plant matter and animal remains of thousands of years of Arctic and subarctic ecosystems, preserved by the cold. In terms of carbon content, the world's permafrost zones hold an enormous quantity of organic carbon, roughly twice the amount currently in the atmosphere as carbon dioxide. This organic material was deposited during and after the last ice age. As the glaciers retreated and tundra and boreal ecosystems spread northward, plant material accumulated in the newly deglaciated terrain. Some of it was incorporated into the permafrost and has been frozen ever since, kept stable by the cold, a vast cold storage of ancient carbon. The permafrost has its own geological memory, its own record of the past. The pollen grains frozen in permafrost. Sediments tell us what plants were growing in the region thousands of years ago. The insect remains tell us about ancient ecosystems, the microbial communities, some of which are still alive after thousands of years of frozen dormancy, tell us about the limits of life in extreme conditions. The permafrost is young by the standards of everything else we have discussed tonight. 10,000 years, 20,000 years, ancient by human standards, a moment in geological time, but carrying in its frozen preservation an archive of the immediate geological past that is extraordinarily detailed. The Great Lakes. We cannot leave Canada's geological story without spending real time with the Great Lakes, those inland seas that define so much of the cultural and ecological identity of southern Canada and the northern United States. The Great Lakes system is geologically very recent. As we mentioned earlier, the basins in which the lakes sit were carved by glacial erosion over multiple glacial cycles. The specific lakes as they exist today began to fill with meltwater roughly 12 to 13,000 years ago, as the last glacier retreated. Before that, the basins may have contained smaller precursor lakes or rivers, or no water at all, depending on the glacial stage. What the glaciers carved into was the rock of the region, including the Canadian Shield and the younger sedimentary rocks that lap up against the shield to the south and west. The Niagara Escarpment, the great cliff of resistant Silurian dolostone that runs from Niagara Falls northwest through the Bruce Peninsula and Manitoulin Island and on into Wisconsin and beyond, is one of the defining geological features of the Great Lakes region. Niagara Falls itself exists because the Niagara River, draining Lake Erie into Lake Ontario, crosses the escarpment and plunges over its resistant cap rock. Niagara Falls is retreating. The river erodes the softer rock beneath the cap rock, undercutting the falls and causing periodic collapses that move the falls upstream. The falls have moved roughly 11 kilometers upstream from their original position at the edge of the Niagara Escarpment since the lake waters began flowing over them, roughly 12,000 years ago. At their current rate of retreat, the falls will eventually erode back to Lake Erie and drain that lake into Lake Ontario through a much shallower channel, changing the entire hydrology of the region. But this will take tens of thousands of years at the current rate. The Falls of Niagara will be roaring long after anything built by modern civilization has crumbled, and the escarpment they are retreating across has been standing for 450 million years, since it was a reef in a shallow Silurian sea. The Great Lakes sit in basins carved from rock that recorded the same shallow tropical seas we have been discussing all evening. The same warm Paleozoic seas that built the Devonian reefs of Alberta were building reefs and carbonate platforms across what would become the Great Lakes region. The same slow accumulation of sediment in warm, shallow water, compressed into rock, later eroded by ice, later filled with meltwater, giving us the landscape we know. The St. Lawrence River carries the outflow of the Great Lakes toward the Atlantic. It is one of the great rivers of the world in terms of discharge volume, and it flows through a geological landscape with its own extraordinary depth of time. The St. Lawrence Valley follows a fault zone, a zone of ancient crustal weakness in the Precambrian rock that has been there since long before Pangea. The Ottawa-Bonnecaire Graben, a rift valley that runs along the Ottawa River and into the St. Lawrence system, is a geological feature that formed during the Mesoproterozoic era, well over 1 billion years ago. It represents an ancient failed rift, a place where the continent tried to split apart but did not quite manage it. This ancient weakness in the crust has been reactivated multiple times over geological history. Earthquakes in the St. Lawrence region, while not as frequent or as dramatic as those along active plate margins, do occur. They are reminders that the old fault zones are still there, still capable of moving, still part of the living geology of the continent. The Charlevoix meteorite impact site in Quebec, visible as a large circular structure near the north shore of the St. Lawrence, adds another layer to the story of the river valley. A massive meteorite impact, roughly 342 million years ago during the Carboniferous, created a structure about 54 kilometers in diameter. The impact shattered and deformed the local Precambrian rock, creating a crater that has been partially eroded but is still recognizable from the air and in the regional geology. When you travel down the St. Lawrence on a ship or look at maps of the North Shore, you are looking at a landscape shaped by multiple geological events across a span of more than 1 billion years. Ancient rifting, meteorite impact, Pangean mountain building, glaciation, the slow carving of the modern river valley, all of it visible to trained eyes in the shape of the land and the composition of the rock. There is one more geological story from Canada that deserves to be told tonight, and it is perhaps the most beautiful of all. The stromatolites of the Belcher Islands. The Belcher Islands sit in Hudson Bay in the territory of Nunavut. They are a group of islands formed from ancient Proterozoic rock, roughly 1.8 billion years old. And in certain formations on those islands you can find stromatolites. Not fossil stromatolites, not the traces of ancient life preserved in rock. Living stromatolites, microbial mats that grow in layered, dome-like structures in shallow water, producing finely laminated rock as they grow. Stromatolites are among the oldest forms of life on Earth. The fossil record of stromatolites extends back more than 3 billion years. They were, for most of Earth's early history, the dominant form of life on the planet. Simple communities of photosynthesizing bacteria living in shallow seas, building layered structures as they grew. They are also responsible for the oxygen in the atmosphere that makes your breathing possible tonight. The cyanobacteria that form stromatolites and their ancient relatives produced oxygen as a waste product of photosynthesis for billions of years. They oxygenated the Earth's atmosphere. They made complex animal life possible. They made you possible. And living stromatolites still exist. In a few places around the world, including the Belcher Islands in Hudson Bay, living communities of stromatolite-forming bacteria are still doing what they have been doing for 3 billion years. Growing, photosynthesizing, building their layered structures in shallow water, quietly, without drama, continuing the oldest continuous biological enterprise on the planet. The stromatolites do not know they are remarkable. They do not know they have been doing this for 3 billion years. They do not know that they once ruled the world. They just photosynthesize. Just grow. Just do the thing they do, as they have always done it, as they will continue to do it for as long as the right conditions exist. There is a profound teaching in that, not a philosophical teaching with words, but something deeper, something about continuation without drama, about doing the essential thing without needing recognition for it, about the quiet sufficiency of simply continuing. Breathe, like the stromatolites, just the essential thing. Continuing. The last geological thought for tonight. Canada is still being made. The geological processes that have been running for 4.5 billion years are not finished. The shield is rising from its glacial compression. The mountains of the west are still being eroded and their material carried to the sea. The Atlantic is still widening. The permafrost is changing as the climate changes. The rivers are still carving. The glaciers that remain are still retreating or advancing depending on the region. The earth beneath Canada is not inert. It is not finished. It is mid-process, mid-sentence. The story we have been telling tonight does not have a completed chapter called Canada. It has a chapter that is still being written. The rock is still forming somewhere, deep in the earth beneath the Cordillera, where magma rises toward the crust. The rock is still being eroded somewhere, every slope where rain falls and gravity pulls material downhill. The sediment is still accumulating somewhere, in every river, delta and lake bottom and continental shelf. The work continues, the story continues, and you are in it, not as a witness to something finished, not as a visitor to a museum of geological history, but as a participant in a living geological story. You breathe, you move, you change the chemistry of the air by breathing. You add your small weight to the ground. Your existence is part of the Cenozoic geological record, however infinitesimally. When humans are long gone, if something intelligent enough to read rock ever emerges on this planet again or arrives from somewhere else, there will be a layer in the rock. Record marked by the chemical signatures of industrialization, the carbon isotopes, the heavy metals, the synthetic compounds, the sudden diversification of certain materials, a geological instant marked in stone that will say, they were here. You are part of that layer, part of the geological mark of humanity, part of the record, however brief, that this planet is still writing about the life that has inhabited it. You will be geological. You already are. Rest in that, in the knowledge that you are not outside the geological story looking in. You are inside it. You are one of its current expressions. One of the ways this ancient land is, right now, alive and aware and thinking about its own deep past. Sleep inside the geological story. Sleep as part of it. Sleep well, deep beneath the ancient sky, on the ancient ground, in the long, long ongoing story of this remarkable and improbable planet. Good night. The night is deep now. The geological silence is all around. But before we truly close, one final thought arrives. A thought about names. Before Canada was Canada, the land had other names. The indigenous peoples who have lived on this land for at least 15,000 years, and possibly much longer, have always had names for the places they inhabited. Names for rivers and mountains and lakes and regions. Names that reflected relationships to the land rather than ownership of it. Names that held stories and teachings and observations about how this particular place worked, what grew here, what animals came through, where the water ran, where shelter could be found. These names predate every geological survey, predate every scientific description of the Pangean history we have been exploring tonight. They are not geological descriptions. They are something different. Relational knowledge. The knowledge of people who lived in a place for thousands of years and learned it in a completely different way than geologists learn it. Not by reading the rock, by living with the land, by depending on it, by paying attention to it in ways that sustained life through conditions that would be very difficult for most people today. The geological, deep time we have discussed tonight is one kind of knowledge about this land, ancient and profound in its way, revealing things about the land that no amount of living on it could reveal directly, because they happened too long ago to be remembered in any living tradition. But the relational knowledge of the First Nations and Métis and Inuit peoples is another kind of knowledge, equally profound, equally ancient in its way, even if not spanning geological epochs. Knowledge of how the land behaves in winter and summer, where the fish run and where they do not, what the sky means when it looks a certain way, how the land sounds different before a storm, what the animals are doing and what it means. Both kinds of knowledge are about the same land, the same Canadian land we have been discussing all evening. Both are ways of knowing a place that is extraordinarily complex and extraordinarily ancient and extraordinarily worth knowing. As you sleep tonight, the land carries both kinds of knowledge, the geological and the relational, the deep time record in the rock, the deep human knowledge in the traditions of the peoples who have lived here. Both are there, both real, both profound. Rest in the fullness of that, in the knowledge that the land you are sleeping on, wherever you are, is known in more ways than any single person can hold, that it is more than any map can capture, that it has more history than any book can contain. The land is rich with knowing, and rich with the unknown still. Sleep on the rich land, sleep deep, sleep well. This is Canada in deep time. This is the land before the name. This is the rock that remembers everything. And this is the night that holds you now at the very latest edge of the very longest story. Rest here, in the now, in the ancient now that holds all the ancient then. Good night.